Hello students, in this video we'll see how to find the volume of a generalized octahedron. We'd like to find the volume, the generalized volume, I'm going to use this notation, of an octahedron in n-dimensional space of radius, let's say, r. Now what do I mean by that? I mean by that we're going to integrate over n-dimensional space, absolute value of x1 plus absolute value of xn less than or equal to r. So what we can note is that at least in two-dimensional space, so if n is equal to 2, what does this region look like? And this region looks like this shape over here. That would be x1 and that would be x2. And if n is equal to 3, this is exactly just the traditional octahedron, right? So we can draw the octahedron like so. So that's our octahedron. And then in higher dimensions, we'll get a generalized version of this. So that's what we have over here. So we have a diamond or a rotated square, then we have the octahedron. And so I'd like to find this volume in general. So we'll have a dx1 through dxn. And we'll use a standard trick. We'll standardize this. I'm going to pull out this factor of r over here by changing the variables. I'm going to let x1 be r y1 and xn be r yn. The Jacobian of this transformation we've seen from previous videos, x1 through xn over y1 through yn, is exactly just r to the n. So we can change this integral over here into r to the n, the n-fold integral over y1 plus yn less than or equal to 1 dy1 dyn. We're going to call this, we're going to find a recursion for this integral over here without the r to the n. I'm going to call this expression over here a of n. So let's find a of n. So to do so, what we'll do is we'll notice that this expression is true if and only if y1 plus yn minus 1 is less than or equal to 1 minus yn. And so what we'll get over here is we can say that this is going to be the integral. So I'm going to just focus on an. So this implies that an is going to be equal to, now where does yn reside? Yn resides anywhere between -1 and 1. So -1 and 1 for yn. And then what we'll have over here is we'll have the rest of the integrals, the n minus 1 integrals, absolute value y1 plus yn less than or equal to 1 minus yn. Then we'll have dy1 through dyn minus 1, and then finally a dyn. Now by the previous result, so what can we pull out? Well, this is going to be an n minus 1 dimensional thing, so I'm going to have this expression over here. That's going to be my new radius of this octahedron. I'm going to have that new radius variable to the power n minus 1 now. So I'm going to pull that out. So an is going to be equal to the integral from -1 to 1. And then I'm going to have what? Then I'm going to have a 1 minus what? 1 minus the absolute value yn. To what power? To the power of n minus 1. N minus 1. And then what's left over is going to be what? Just the an minus 1. So an minus 1 dyn. And so now, of course, this is an even function. So this implies over here that an is equal to an minus 1 times 2, the integral from what to what? The integral from 0 to 1 of 1 minus yn to the power n minus 1 dyn. So let's integrate this and see what we get. So now integrating this, we can conclude that an is equal to an minus 1 times 2. And then this is going to integrate to 1 minus yn with a negative sign. 1 minus yn to the power n over n from 0 to 1. And we say it just gives me a 1 over n. So this implies that a of n is equal to 2 over n n minus 1. And this is going to give me a factorial relationship with a whole bunch of powers on 2 on top. So we can see that this implies that an is going to be equal to, if we turn this down all the way down to what a0 will be, which is easy to compute, we'll see that an is exactly going to be 2 to the n over n factorial, right? In particular, what we can see is if we looked at a equals 1, we can see that when n is equal to 1, you have a answer of 2, right? Because you just have integrating from -1 to 1 of just this line segment over here. So of course, when n is equal to 1, you're going to have a what? You're going to have a 2 over 1 factorial, which is 2, so it works out. So it satisfies the initial condition and the recursion. So we have an is 2 to the n over n factorial. Therefore, the volume of this generalized octahedron, O(n) of r, is going to be r to the n times 2 to the n over n factorial. And in particular, when n is equal to 3, we can find this. Let's take r equals 1 as an example. If r equals 1 and n equals 3, so if r equals 1 and n equals 3, that gives us our classical unit octahedron. So the unit octahedron will have what volume? The volume will be what? So r is equal to 1, and then n is equal to 3, so that's going to give us a factor of 8. So we have an 8 over 3 factorial. 3 factorial is equal to 6, so this just gives me 4 over 3. Thank you very much.